Thank you very much. How much have you guys covered so far in terms of directional fields? Okay, you haven't covered anything at all so far. Okay, what have you covered? Okay, only 1.1. Perfect. In that case, let's start with 1.1. Start with something you know, and then we'll move to something that's slightly less familiar. Need to make sure I'm opening the right document. Yes, I am. Link address. I hope that that actually works. So yeah, let's start with chapter 1.1. Then we'll go along and we'll work as we go. And if you guys have questions, we'll work with things from there. I'm just wanting to find where I've started because I made some notes first to try and make life easier. So let me start by sharing screen as well. Creation screen thingamajig. Let me just start on a new page. Can you guys all see this? You aren't going to have a TUT test. If it's anything like how we operated last year once we went into a remote, you should have a number of tests and mini quizzes along the way, and they'll make up your mark. Not to say that the tutorials aren't valuable. I would highly recommend you do do some of the questions beforehand, as it really does help. But let's start with the first question. First of all, before we even begin, were there any problematic aspects that you guys came across, or are you struggling with any of the terminology? Because I think to start with, let me go over some of that because the terminology is very important. So first key thing is when we're talking about linear, we aren't submitting anything today, no. When we're talking about linear and we talk about order. So if we're talking about a linear differential equation, we're talking about y prime. So I'm gonna put P, Q, and R. These being P, Q, and R are functions of X. So if we're talking about linear, we can have any number of derivatives of y, but the important point is they're all to the power of 1. None of them is of a greater power. If that is the case, then we're talking about linear. In terms of order, we're talking about the values over here. So in this specific instance, we've got a second order differential. So our order of the above would be 2. If we were to have y prime prime, let me turn off auto, y prime prime squared plus y prime equals 0, it would be a second order, but it wouldn't be linear. It wouldn't be second order, not because of this, and it's linear, it's non-linear because that is a 2. Right hand. That's what that noise is. Thank you. I just need to pull. I see hands. Sorry, I don't actually know how to see if people put up their hands very easily. But these are the key points. Okay. So, okay, I'll go over that again quickly. In terms of the key terminology you need to be considering, linear is assuming every single one of these is to the power of 1. If it's to a greater power, then it's not going to be linear. So your first question, which states, let me pull it in. These are, here we go. So our first question, which says, is it linear or nonlinear? It is wanting to know, once we organize it into our set form, which I'll get to in a moment, is wanting to know, is is our variable that we're looking at got a higher power than 1, or is the highest power 1? And then the order is what degree of derivative is the equation. So you say nonlinear because you think of the y squared. Well, first things first, with an equation like this, we need to get it into a workable form. Our workable form that we always want is going to be y to the nth prime, and we're always going to have functions. I'm going to start with p of x, y to the nth prime plus q of x, y to the n minus 1th prime, all the way down to y prime with, we'll have a function here, say theta plus y equals another function there. The session is being recorded, yes. So the way that the equation that you're currently going to be looking at, you're normally not going to be going up to the nth order, but in this case, we need to get it to the order where it's probably going to be first, second, or third order in terms of what you're dealing with at the moment. Sure, let me quickly enlarge it. Please, can this work? Nope, that didn't work. Ooh. Sorry for the stretching, but it is still readable, I hope. So because we want all our y's on the one side with a function of x times a y to an order plus another function of x times y to an order, it will be downloadable, don't worry. Because that's how we're wanting to get it, our final equation, what we want to then do is, first of all, to the board and above the chat, let me just pull up. It is recording, yes. So let's now take this equation. We have y squared minus 1 dx plus x dy. Oh, that's not typing correct. I'm not writing correctly. X dy equals 0. So there are two ways we can go about this, and always remember this. We can try to get this equation in terms of x, or we can try get it in terms of y. It depends on how we're wanting to go about things. Most commonly, you guys are used to writing things y as a function of, so y as a function of x, but it is also possible to write x as a function of y. Both of these are valid ways of going about this. The first important point is we need to get the differentials either grouped together or out of the equation entirely. To do that, let me just move down if it will let me. So to do that, we want to move this this part of the equation over to that side. So we're going to have y squared minus 1 dx is equal to minus x dy. So now that we've got that, we want to try, we know how to work with a dy by dx. Working with just a dx or just a dy is not the easiest thing in the world. So now we're wanting to, let's start by moving the dx to the other side. Now we're going to have y squared minus 1 is equal to minus x dy by dx. Now we can quite easily move the x back across. So now we have y squared minus 1. Just want to make sure I'm not missing something here. Y squared minus 1, 1 over x is equal to minus dy by dx is y prime. So now we're able to rewrite this as, let's move everything to the left-hand side to try match our form that we're used to. We can now have y prime plus 1 over x y squared minus 1 over x equals 0. Now this part over here, we can move over to that side, which would get it to our ideal form, but we can still see from this, we have a y squared here, so it is it's going to be non-linear in terms of y. Can you still see my picture? I see it's just dips. My connection dipped a little bit.
Yes.
Okay, perfect. Thank you. So yeah, we can see that it's non-linear and it is of order 1 in terms of y. We aren't done with the question though, because there's the other way of looking at it, which is x as a function of y. So if we're wanting to do that, we can take this section here and let's work with it over here. So this time, instead of looking at dy by dx, we're going to be looking at dx by dy. So now we have y squared minus 1 dx. We're going to bring the dy over this side. So we have dy is equal to minus x. Now that, if we want to separate, we want to now isolate the dx by dy, we will come out with y, sorry, and we will come out with dx by dy equals minus x over y squared minus 1. We move the dx by dy across, and we will land up with 0 equals, we want our x prime, which is dx by dy. So it's going to be minus x prime because I'm moving it to the left, minus, then we will have 1 over y squared minus 1 times x. And this we can now see in terms of x, that the x here is to the power of 1, the x prime is to the power of 1, so we can say that this is linear. And we can also say that it is of order 1, so it's first order. Do you guys follow that? Mangani, where did I lose you? Okay, so in terms of, if we go back to what we started off by discussing, here we go. Linear, we are looking at each of our I'm trying to remember. Is it not first order 2? So I just want to pull up one document here quickly. I want to see if I have a nice little diagram for you. Okay, no, I don't actually have that anymore. Okay. So in terms of when we're looking at it in terms of y, the last step. Okay, let me just start with Mangani's question why it's linear. So what we were looking at in terms of the a linearity is when each of the so here we're talking about it in terms of y, when each of your y's, your y prime, your y prime prime, etc., when each of those is to the power of 1, it's going to be linear. If any of them is to a higher power, if they don't specify, you have to do it for both, yes. In your tests, because there is more time restrictions, and also because they're generally wanting to cover more content, they'll specify almost certainly. I actually don't recall there being any of the past papers where they didn't specify. But yeah, because each of these is to the power of 1, this would be linear. If any of them is to a higher power, it'd be nonlinear. In terms of, and then order, it's what is the highest number of primes. So is it possible to linearize higher power? I'm not going to say yes, Koza, because I'm sure there are instances where it can and where it can't be done. A lot of times, not really part of it. Yeah. At present moment, you're not really going to be too concerned about that. Absolute value of square root, how would that change the linearity of the equation? So if you had y to the power of a half, for example, let's say your equation came to y prime plus y to the power of a half equals 0. This would be nonlinear because of that half there. Similarly, if you had y prime to the power of a half plus y, this would also be nonlinear. Each of these has to be exactly 1, no more, no less. It's also important to note if you land up with an equation which is y prime, say, plus y equals 0, this would also be nonlinear because these two values of y are multiplied together. You can't separate it into a linear combination of orders of y. So if we go back to our question over here, the reason why it was linear, well, the reason why it was nonlinear for in terms of y is because we had, let me make sure I'm using a color, we had this over here. That y squared tells us that it's nonlinear. So that immediately informs that. Our prime there, we don't have anything higher than that. That indicates that it would be first order. When we do it in terms of x, we land up with an x prime. We make y the subject, and the first question is not correct. That's correct. If you make y the subject, the first question is nonlinear. Because remember, you're always looking to get to a linear combination of orders of y. So something times y prime plus something times y plus something equals 0, or you'll often land up moving that part to the other side. The common form that you'll cover soon is p of x times y prime plus q of x times y equals 0. You'll cover this. This is how you'll be given, or how you'll be wanting to work your equations out in that form. The reason why we use this form is because it's easy to manipulate. We aren't having a tutorial test, no. But I just want to double check. So there, have the question. Yeah. Okay, I hope I've covered most of the questions there. Grid on the page? Sure. Let me see if I can. Sorry, this is the first time I'm utilizing this software. I'm hoping that it's going to be better than what I used last year. Let's try for all. Apply to all bit. Paper style plane. Ha! There we go. Hey. Yeah, sorry if my lines go a bit squint now, though. Okay, there is a very important. So why it's linear? Okay, let us do another question, and maybe that'll help address that. So let's take the next question here. Let me. So is sine theta y prime 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 minus cos theta y prime equals 2 linear or non-linear? And what is its order? So let's start with linear or non-linear. If we want to look at this, we can rewrite it as sine of theta times y prime 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 to the power of 1 minus cos theta times y prime to the power of 1 equals 2. Because both of these are to the power of 1, it's going to be linear. Now, looking at the order, what would you guys say is the order and why? Perfect, yeah. It's third order, and this one is linear because each of them is to the power of 1. Because if we want to write this in terms of our method that we want, where we'll have a function of x, so we have p of x times sine times y to the prime prime prime, p of x is that, then we would have plus 0 times y prime prime, because we got nothing for y prime prime, plus cos theta would be your q of x times y prime equals 2. We take 1 over y squared as a function like q in the form of r. So yeah, as Rajana's saying, when you work out, which part is that? 1 over y squared. When we work out, we come out with this over here. And this minus 1 would be your p, and then minus 1 over y squared minus 1 would be your q. And x prime is to the power of 1, x is to the power of 1, so it's linear, and it's first order because we only have up to 1 prime. All these questions are very, very formulaic and follow the same pattern throughout, which I know, having done the subject, is a very big relief for doing the problems. Um, so there's something I want to point out. If you look at question 4, 5, and 6, it asks you to verify that, and then it gives you a series of values. Is the chapter after this 2.1? Yeah, we will cover 2.1 after this. So yeah, it asks you to verify. Now, very, very important here, and this will save you time in an exam as well. When it says verify, that means you're simply wanting to check it works. So in this case, let me pull in a question. It bothers me it pixelates so much, but what can I do? So very, very important. When it's saying verify, you are not needing to take this equation and start solving it to get to this. You aren't going to start here and move there. When they're saying verify, they're saying this is an equation. Wait. They're saying this is an equation, and we want you to check that it works when you plug it into this. The reason why I say this is very important is you may well be able to go from the y prime prime plus y equals tan x to the y of x equals. You may be able to do that, but it'll take you 4 to 5 times as long. And in a test, that will cost you a lot of time and it'll cost you a lot of marks as well. So whenever you see verify, nice and simple methods. They have given you, let me go back to black. 1, they've given you y of x equals. The answer to 3 second order in terms of x. I have double checked those. Let me, so I'm just going to pull up my notes quickly. Question 3, you say. 3 is second order and it is nonlinear. Sound is horrible. Okay, let me see if I can address that. Okay, give me 1 sec. I will, because I was trying to run it across 2 screens. I will try. Let me also give me 1 moment. I will sort out sound setting here. Okay, is that better? I've just switched out driver. Rather. I am. I'm just pulling up. Okay, if that's the case, I'm just going to pull up the window again so I can see neatly. How to go about question 4. Is this the one that I've got up at the moment? The verify. Okay. So what we're wanting to do here, step 1, we have been, and this is going to apply for all of these questions where you have verify. You have been given y of x equals something. So in this case, we've got minus cos of x, ln of sec x plus tan x. Now, if we look at our equation over here, we have y prime prime and we have y. So We know the nice part is we know how to do differentiation because we've all done pure or engineering maths last year. I believe you guys are all engineers, so you've all done engineering maths last year. So first things first, we need to work out what y prime prime is. So easiest way to go about it is to work out what y prime is. So I know it might feel a little bit tedious, but calculus can be fun, and I know you guys won't agree with me there. So we're going to do chain rule here. Let me just put brackets there. Our chain rule, this is our f, this is our g. So f prime g plus g prime f, we will come out with sine of x plus verify it without its interval. Yeah, we should be able to. We're verifying this one without its interval. So yeah, if we cleaning that up. So if we do this, so if this is our f, this is our g, f prime g plus g prime f. So f sine x times ln of sec x plus tan x, f prime g, plus now g prime f. So ln, the derivative of ln of this is going to be it's going to be sec x tan x plus sec squared x all over sec x plus tan x multiplied by minus cos of x. You won't be asked to graph the solution curve, don't worry. That would be hell. Now, we could just go about working out the next derivative, but this isn't looking too nice to me, so I'm going to simplify. So the first bit will keep the same. Sec is one over cos, so if we multiply the cos in here, let me just bring the minus out to the beginning. So multiply the cos in here, 1 over cos times cos, we will be left with tan of x plus sec x over sec x plus tan x. That we do need an interval of definition for these variables. Can we assume the interval? Yeah, that's a good assumption. That would be a good assumption. I'll go over and I'll double check that and I'll get back to you next week with regards to the interval. But yeah, so if we multiply the cos in here, we come up with tan x plus sec x over sec x plus tan x. These two are equal, so that is going to be minus 1. So if I just that, I'm just going to do this because I don't like to write much. So we can then rewrite y prime is equal to sine of x ln of sec x plus tan x minus 1. Then now we still need y prime prime. We can once again do some fun differentiation, and we will come out with let's see, we'll come out with cos x ln sec x plus tan x plus sine x times, it's going to be the same as what we had up there, which should be sec x tan x plus sec squared x all over sec x plus tan x. Now, sine times sec is equal to tan. So once again, we can pull a sec as a common factor out of there. Sec is 1 over cos, so then we can take that out and that out. Once again, the inside of this becomes 1, and we are left with cos x ln of sec x plus tan. I'll go back to that in a moment. Tan x plus tan. So you wanted me to go back to, wait, where's my mouse gone? There. So we wanted to go back to here. So if we are going to do the y prime, we're going to, if we consider f is minus cos x and g is ln of sec x plus tan x, we know by product rule that it's the derivative of y is going to be f prime g plus g prime f. F prime, so the derivative of minus cos x is sine x multiplied by the g, which is, so let me just do that and that. So derivative of f plus, multiplied by g plus the derivative of g, where's my thing? There, derivative of g times f. There was a hand.
So
Yeah.
no, after you finished explaining this, I want to ask a question on the second slide.
Sure.
So now you can take it down.
Sure, let me just
Scroll
do
down,
that.
scroll down, yeah. So let's say you had y prime is equals to sine x ln sec x plus 10x minus 1. And then from there, you got the first part, cos x ln x sec x plus 10x. And then from there, what happened to that negative?
I might have missed something. Oh, when we're doing the derivative of this.
Yeah. Yeah, it's a
Okay,
good
so derivative of a constant is going to be 0. So remember, if you go
okay.
d by dx of 5, for example,
Oh,
is going to equal 0.
no, say you're
Don't
right,
worry,
you're right, you're
we're all
right,
rusty.
you're right.
We're all rusty, don't stress.
Yeah.
So yeah, once again, we then land up with our y prime prime coming out here. So now that we've got the tools that we need. So if we go back to our question, we've got our y prime prime, we've got our y. All we have to do now is plug into the equation. So it's just simple substitution. So we have y prime prime. I just want to double check. Is it y prime plus? Yeah, plus. Y prime prime plus y equals tan x. So we have, put a red bit there, put a green bit here. We want, oh, no, that's not the right place. We need put green here. We've got the green for this, and we've been given the equation. So I'll put blue for this. There's another hand, Koza.
So I wanted to ask y prime, which is the minus 1, how did you get it?
Okay, so if we go to this, so do you follow where we got to at this point here?
Yeah, I understand that point.
Okay, so we've got that minus over here, which I'm going to move to the beginning here. So that's going to be a minus here. Now let's multiply cos x into the brackets. Cos x multiplied by sec x tan x. Sec x is 1 over cos. So cos multiplied by 1 over cos is 1. Now we need to multiply it into here as well. So cos times 1 over cos squared is going to be 1 over cos, which is sec x. So what we land up with is tan x, got 1 multiplied by tan x, plus 1 multiplied by sec x, divided by sec x plus tan x. Because the numerator and the denominator are equal, we can say that this is equal to 1.
Okay, I get it. So to get to y prime, to get the one that is below y prime, you did what, the derivative or what?
To get the y prime prime, you get the, okay. So remember, y prime prime is equal to d by dx of y prime. It's the just the second derivative. Sure, no problem. So now let us do some substitution. So our y prime prime, we have cos x ln of sec x plus tan x plus tan x plus, now our y, yeah, spot on. I'm sorry, I'm not great with names. That Clomisa. So if we go pull out our y, it's minus cos x ln of sec, okay, plus, okay, minus cos x ln of sec x plus tan is equal to tan x. And they're asking us to just verify. And let me have a look. We've got, okay, Cosa or Deboro?
Sir, can you please look
Yeah.
at the second derivative there? How did we get to tan of x? How
Okay,
did we
sure.
get to cos of?
Okay, I will do that very quickly here. So I did land up missing a step in the process. So let me, the easiest way of doing this. Sorry, this thing is not being very cooperative. So when we are doing the derivative of this, we once again are going to be looking at in color, looking at product rule again. So derivative of sin x is our cos x, so that's our f prime, and then our g becomes that, and then our so I went about doing this. Let me take my eraser and I'll just take that. So then if we do the derivative of ln of sec x plus tan x, that will come out, will be, it's going to also be a chain rule. So the derivative of ln of something is 1 over the content, so 1 over sec x plus tan x times the derivative of the inside. The derivative of sec x is sec x tan x, and the derivative of tan x is sec squared x, multiplied by sin x. So if we can then also multiply that sin x into here. We can either do that, or we can, what actually will be easier is to say that this is equal to sine x multiplied by sec x tan x plus sec x over sec x plus tan. So pull out a common factor in the numerator of sec x. Do you follow?
Yes, I got it. Sec is 1 over cos, so it's gonna be sine over
Yeah.
cos, then you get tan. Oh, thank you,
Spot on.
sir.
Spot on. Yeah, you guys you may need to just go over a bit of your calculus from last year. Particularly in applied maths, you'll be using it a fair bit. Third order. Okay, I'm just going to check the time. Okay, I'll go over that. Mokwena, I'll go over that very quickly. And then I really want to move on to the next section just so that we cover everything. But once again, just as I'm so sorry if I'm mangling your name, Mfadzweni is saying, negative, because the negative cos here is for the y which they gave us at the beginning. Verify y of x is equal to minus cos, etc. there. But yeah, so as has been said, this is then just you're going to then just have to calculate this, and you can actually quite easily see that this cancels with this, and you land up with tan x equals tan x, and it's verified. But just to give you a quick set of rules. One, if you're told verify, start by taking your y of x and get and you need to do a derivative to get y prime, whatever it is that you have in your equation. And then your second step is substitute. It's substitute and check. And you may well get a question where you are asked to verify and you come out with tan x equals negative tan x. And you'll then know that when you're trying to verify, it's not true. So don't always assume that it is true. Just do bear that in mind. You asked, rewind to question 3, the second order nonlinear. Let me have the question here. It's not necessary to show all the derivation step of all the steps of the derivative, but show as many as you need to not get lost, and also show enough to show that you actually did do the derivative, and particularly because your tests are online, yeah, verifying is making sure that the equation holds true. Yeah, you were asking, find it to be second order function. Y prime to the power of 3 isn't the same as y prime prime prime. You are correct, Makana. It is a second order equation. And it is nonlinear as well. I want to go over, so this stuff, basically all these questions are going to be pretty similar. Sometimes you may have to use implicit differentiation, sometimes you'll just have to use normal differentiation, but by and large, they're all pretty much the same. So I want to go over a little bit of directional fields with you guys, because it looks like a scary topic, but it really isn't. And the sooner you start getting a feel for it, the better. So if we look at I'm going to look at the directional fields question 1, which states, sorry, my computer is very slow at the moment. Okay, it states, basically it says you've been given a directional field, and then sketch by hand an approximate solution curve that passes through each of the indicated points. Use a different colored pencil for each solution curve. Once again, there is something quite important to note within the question. They are stating approximate solution curve. So if you are a little bit off here and there, you really don't need to worry. It's the general curve that you're looking at. Now, the next point they mention is it has to pass through each of the indicated points and use a different colored pencil for each solution curve. What that means is you aren't going to have a single curve that passes through all the points. You could have one that passes through multiple, but you probably won't, especially if they're asking you to use different colors. So this graph over here is what they're saying you've been given. And what this graph represents, each of these arrows is representative of the gradient at that point. You've been given an equation of dy by dx equals x squared minus y squared, and you don't know what the actual equation is. You have just been told, and it is possible to work out what the derivative is at each and every point. So it means that there are an infinite number of curves that could fit the equation dy by dx equals x squared minus y squared, which is why they're asking you for multiple options. What makes these questions very nice is this is a qualitative analysis. You'll probably hear Dr. Vizaya talk about this as well. When it comes to qualitative, you're looking at, as the word suggests, the quality of it, as opposed to a specific value that comes out. You will also look at directional fields a little bit in terms of a quantitative analysis, where you're going to need to know and work out the actual values. But if you're given a directional field like this, they're just wanting to know roughly what the thing looks like. Where this would come in handy is if you've come out with a bunch of data from an analysis and you want to know roughly what it'll look like, just to get a feel for what the relationship is between your X data and your Y data, you can then start looking at it in terms of this. So first thing to notice, you're given a point point y of 2, but y of minus 2 is equal to 1. That means your 1 is your y, your minus 2 is your x, because everything here is given in terms of y as a function of x. So the reason why these are really nice is this point over here indicates where are we starting? What is your point? So if we go to y equals 1, so we're going to be somewhere over here, and x is equal to minus 2, somewhere over here, that gives us this point here. Now, all you need to do for this is basically follow the arrows. It's not a trick question. It's simply follow the arrows approximately and draw it neater than I am because I'm doing this digitally, and you'll come out with a curve like that. Your next curve, y of 3 equals 0. So our y is going to be 0. Our x is going to be 3. We go to this over here, and we would get something that looks roughly like this. Because it's approximate, remember, you can be more or less. One person's maybe look a little bit different to another person's, but by and large, they're going to look roughly the same. The key thing is make sure it passes through the points that you have got here. So for example, make sure that it's passing through this point and make sure that the red one is passing through this point here. and make sure that it's following the gradient curve. In terms of the first 4 questions of this, that is literally everything that you would need to do. If you're given a directional field, then all you need to do is fill in the curve. If we were to, I'm just going to do the others for completeness sake. X being 0, Y being 2. We've got this. It'll come down here and roughly up there. And the purple, 0, 0, something like this. So in terms of these, you don't really need to mark where your point is. You're just needing to draw in that curve. If you are given a directional field and you're asked like this is free marks. I'm telling you right now, it's free marks. You may have 1 question or 2 questions like this in tests. More likely, you're going to be given something along the lines of question 5, 6, or 7. Now, that is, I'm going to go over this, and I'm sure Dr. Vazaya will go over it as well with you guys. Let me go to a clean sheet. Page, new page. Work. Yes, it works. The type for directional fields should be called, let's have a look, 1 first TUT problems directional fields. I will go over, you asked me to go over it again. So basically with this stuff, if you're given a directional field, the hard part has already been done for you, which is creating that field of lines, which is where this comes in. The rest of it is just figuring out where your point is and then following those directional lines. And following them is just approximate, which is why you don't need to indicate where you cross axes. You just have to show an approximate curve. So long as it's vaguely close to right, you'll be getting the marks. Creating that directional field. This is where we transition over for a little bit more towards quantitative. But once again, we are looking at a nice little process. So first thing, we need to check, is it in a usable form? And our usable form is dy by dx is equal to f of xy. Surely I've been told I need to cover directional fields with you guys. Covering it, even if Dr. Vazaya hasn't gone over it yet, it will help to be able to see it in advance. This over here is the form that you want for your directional fields. You want your derivative is equal to a function of x and y, or x or y. Remember, f of x comma y can still be something like this. In this case, our y is not involved. So is it in that form in this case? Yes, it is. 2, we need to make a table. And that table, because doing it on a computer will give you nice, evenly spaced lines like this, we as humans are not that patient, and we can also imply what things would be roughly in between. There's a nice little guide that I'm going to give you here, which will should by and large help you across the board. So let me just make a little table. That one. Let's turn that off. So now we want to have an algebraic relation. So now this, what I'm meaning by this is we're going to state x, we're going to say x is equal to y, if that is the case. Next, we're going to have x and y, our two coordinate points, and then we're going to have dy by dx, which is equal to our f of x, y. And finally, I'm going to say graphic. This is just a graphic idea of what's going on. So our first point, we're going to say x is equal to y. So in this, our f of x, y is equal to x, because that is what it is over here. So our algebraic relation xy is going to be x because we've decided x is equal to y. If we have this f of x, y, if x is equal to y, we don't have a y, so x is equal to x. So it will just be x. What that means is our graphic, we would have a parabola. And you may be wondering, why is this a parabola and not anything else? And that's because if we have dy by dx is equal to x, if we were to integrate this, we would come out with y is equal to half x squared. Yep, half x squared. It's because at every single point along the curve, if x is equal to 2, then the gradient is equal to 2. That's what we're saying. If x is equal to 3, the gradient is equal to 3. Going to double check that this lands up. Yep, that works. From the beginning. I'm not going to be able to go to things from the beginning for this because we are going to run out of time, but I'll go through as where we get the algebraic relations. These are just some general things to, and I'll show you where we get them actually on the side here. So let me make. So when we're going to be drawing our graph, we want to know along our axis what is going on. We want to know going make it nice, please, program. Okay, okay, and we want to know what it's going to look like along these lines, basically, pretty much. So here, I've this one over. Let me flip back to data ruler. This is x equals y. We're also going to do x equals minus y. We're going to do x equals 0, and we're going to do y equals 0. So, and that will cover your fields quite nicely and clearly. You can do more. You can do y equals 2x if you really want. You can do 2y equals x. But generally, these 4 are all that you'll end up needing. So our next we would do is x equals minus y. So we would have x minus x. We substitute into this equation, into our equation here, which is just simply x. Still come out with x, and our graph is still going to be a parabola. Then if we go x is equal to 0, we assume that. Then we have 0, y. If x is equal to 0 here, then we have 0. Our graph would just be a horizontal straight line because there's no climb or drop in gradient. Finally, if we say y is equal to 0, then we would have x0 dy by dx. Because it's just x, we would still come out with x, and that still comes out as parabola. First x. Yes, it is. Thank you. Thank you. I did miss that. You have to integrate the equation to get an idea of what the graph will look like. Well, let me show you what we've landed up doing here. Because we have got these values, in each of these cases, if we know dy by dx is equal to x, therefore y would be equal to x squared over 2, over if you really wanted to know what y is. But because we're just plotting the gradients, because directional field is just a series of gradients in a Cartesian plane, let me flip to a new color so it'll be easier to see. It actually lets me scroll down as well. Okay, so what we know is, let's start with x equals y. So we know that our gradient is equal to x. So when x is 0, we know our gradient is a horizontal line. When x equals 1, we know it's 1. X equals 2, it'll be 2. 3, so it'll get steeper and steeper. And then here, we know that when x equals -1, and it gets steeper and steeper in that direction. We look at the going the other way, when x equals, again, we've come out with x over here. So it'll follow exactly the same type, except drawn neatly. Exactly the same type of thing as you see above. It gets steeper and steeper until it gets shallower and shallower going in this direction. Again, this is very difficult to do digitally, unfortunately, but you do understand where I'm coming from. We have a look at x equals 0. So this is along the vertical line. We know it's a horizontal line. So at every point along this, it is a horizontal line. The nice thing is where you have the intersection, you can just double check. You can see, well, is this matching the other ones? And it should always. You shouldn't ever come out with it being at one angle with along one line at a point and another angle at the same point where it intersects from another. If you do find that, then you've made a mistake somewhere along the line. Going the other way, we will find out that once again, all of this lands up lining up like that. And what you can land up seeing is, let me pick a different color. If you want to just draw a curve following these lines, you'd be able to, and you'd come out with a parabola. Similarly, if you draw it in crossing 0, you come out with a parabola. Getting to the next part of the question, they have specifically asked for you to draw a curve at y of 0 equals 0 and y of 0 equals -3. So once again, just like in the first part, let me erase those purple lines. So let's do y of 0 equals 0. So once again, 0 and 0 is our starting point, which is the origin. And we just need to draw a curve that roughly goes through the lines. The last parabola was much prettier, but you get the gist. Something along that. Now, if we want at -3, so x is equal to 0, y is equal to -3. We go to -3. We should still get a parabola looking roughly reasonable. And that's as simple as it is. This section over here is the hardest part of it. Basically, I mean, I've got another example. If you look at example 7, it's a little bit, it is a little bit cleaner to resolve, because here your equation you're given is y dy by dx is equal to minus x. First thing, is it a usable equation? At the moment, it isn't. At the moment, we've got a y next to the derivative. So now we want to convert it into a usable equation. So dy by dx is equal to minus x over y. So now we have our f of xy, and we have our derivative over here. I'm going to actually, just to make this easier, we're gonna match exactly what we've done over here, and I'll just erase the contents of these. So now, if we have x equals y, our equation now here is going to be minus x over y. So if we substitute x equals x and y equals x into this, we come out with minus 1. If we substitute x equals x and y equals minus x, we come out with 1. Substitute x equals 0, y equals y. Minus 0 over y is equal to 0. And then if we substitute x into equals x and 0 equals y, we come out with undefined. Now, if you ever come out with undefined on a 2-axis graph, you know that it is simply straight up and down. If it's 0, it's left and right. If it's 1, well, we know what that is. It's climbing by 1. And if it's minus 1, it follows like that. So our x equals y, I'm going to do a new little graph because the other one's a little too messy to erase on. So let's start with our... So by the way, you don't have to draw these lines in. If you're doing it by hand, I'd recommend you do that lightly in pencil just for your own reference. Let's do... I need to get rid of the ruler. Let's do this one here. So x equals y. Along this line, our gradient is minus 1. So gradient is always going to be minus 1 along this curve. This right? I feel like I might have missed something. I actually see something that is going to be relevant to mention. Ooh, that was without ruler. So if we're going the other direction, we are now looking at this equals 1. Now notice we have, at our origin, we've got 2 different directions going on. Both directions are working out. One is 1, the other is minus 1. So at the back of your head, start taking note of that something might be going on at the center. There might be an issue. Before we assume there is, let's look at the other gradient. So let's go when x equals 0. What is our equation? So that is our vertical y-axis. So here we come out with horizontal lines. And then our final one, when y equals 0, so that's our x-axis, we have vertical lines. So immediately you can start to see we're getting a circle pattern emerging. So we can quite clearly see that what's going on is something along the lines of this. We have circular graphs appearing, not offset like that, but we've got circles. Now, what's very important to note with that is at that center, we don't actually have a gradient. It's undefined. The value of our equation is not going to be defined at that center point, and that indicates why we have gradients that aren't making sense at the center. So what we can identify there is there isn't a curve that exists at the center that has a derivative, or at least has a gradient. And that would make sense since we know that the curve is a circle based on our lines. We know that x squared plus y squared equals 0 would be our only curve, and that in itself is not really something that's terribly functional. But yeah, again, they have asked in the question for y of 1 equals 1 and y of 0 equals 4. So y of 1 equals 1. Let's say that this is 1. So that would be 1 and 1 over here. And y of 0, so that's x, equals 0, y equals 4. So that would be a larger one, something like that. And that would be, I'm not sure, maybe 5 marks? It's, again, directional fields are very formulaic, very, very straightforward. They do look daunting to begin with, and they are a pain to draw and sketch, but do remember that all the people who are going to be marking your work have done the stuff before, and we're well aware of how painful it is to sketch. Okay, first two columns. So think of the algebra. Okay, let me first start with Kahwa's question. How to plot the sketches. So what we're doing, in fact, that links to Leong's question as well. I'm going to go back to an aspect here and talk about the two aspects of a vector field. The vector field, you're looking at a series of points and the gradient at those points. So your series of points are going to be defined according to this, and the vector or gradient at that point is defined according to this. The algebraic relation this is just a tool. It's a tool to figure out what this field looks like. Because if you have if you have a set of axes and you know that things exist within that, you want to know how does this field act. You know that somewhere along the line, the field will probably look maybe something like this even. But you don't know really where to begin to start plotting something like that out. You could decide to create lines like this and work out what the gradient is along each of those lines. But again, that's going to be quite time consuming, but it is still possible. It could still give you a way of going about it. The algebraic relation, the reason why we do it like this, why we land up saying, let's figure out we're basically creating an equation to discover what the gradient is if we were to plot points along this line here. So along this line here, the equation for that is y equals 0. So that would be this one over here. And when we say y equals 0, if we're substituting into an xy system, because we need to put it into an xy system to be able to accommodate an f of xy, we're saying y is equal to 0, x is equal to whatever x is. So x remains constant. The reason why we're doing this is figuring out what the derivative is. If we know what x is and we know what y is, it's going to be incredibly difficult because we've got two variables. If we restrict it to one variable, it's going to be much easier to work out. Does that help in understanding? Yeah, so the algebraic relation, it's just basically making a star on the graph. By making a star, it means that across, because most of your stuff is going to happen near the origin, it means that you've got a series of data points that are quite near to each other that will help indicate what's going on. It also helps by having the x and the y. It also, the y equals x and y equals minus x sets of points. It really helps to use those, because through doing so, you're going to come out with probably start to see some patterns emerging, which you wouldn't necessarily if you just did a set of grids of lines to work out the points. Yeah, exactly right. Making a star makes everything a lot easier. I do know, I do understand that it is Friday and it's quite, you guys are probably feeling quite tired. Because of that, I don't think I should go over separable differential equations. Dr. Vizaya asked if I could, but only if we had time. I think it'll probably, I don't want to overload you guys in terms of new info here. Generally speaking, separable differential equations are, it's the natural progression from your section 1.1. It's, you actually will find that what you are doing in places, for example, like this, where you are moving the dy by moving the dx to this side, you're pretty much doing what you're going to be doing in your follow-up section. It it's you'll I know the content moves very quickly. I'd recommend you try to keep up with it and just keep making notes and keep practicing. The tutorial, you should also have a set of solutions uploaded with the tutorials. Why is undefined a line facing up? Okay, so that's a very nice question. So if we have undefined being a line going straight up, we're basically saying it's, I don't know, ruler, it's something divided by 0. I'm going to go k divided by 0, where k is a number, a positive number. If we divide, if we think of that more in terms of k divided by x, where we're doing the limit as x tends towards 0, positive. If you think of it in terms of that, that is going to equal positive infinity or unbound above. And that indicates that you're going to have a line going vertically. This is the nearest representation that we have to k divided by 0, which we know is undefined. So we know that it's going to be a vertical line in terms of gradient. Are they not available to you at the moment? If they aren't available, I can, okay, cool. Yeah, they are a bit mixed up. Yeah, the prerogative from Dr. Vizaya is that all of you should be able to have access to the solutions as well, because it helps. It really helps you work and study on the stuff. And yeah, like the point of this stuff is for you guys to understand, not for you guys to struggle through it and then only get the solutions near the end. That said, don't just study from the solutions. I can attest that from my first test that I wrote, it's not a good idea. Work through the stuff yourself and then check yourself with the solutions. If you're getting a bit stuck, go through the solution, the worked solution for that question, then try continue on your own. Are there any questions specifically on the stuff, or also equally importantly, is there something that I can do for the next tutorial session that will make this better or easier for you? I really appreciate that. So generally speaking, if you guys have questions on this stuff, in fact, do you guys have a WhatsApp group for this already set up? I believe I have a couple of your guys' numbers from last year's WhatsApp group. If one of you could just PM me the link, I'll join us, and that way, if you guys have questions on the material that you'd like answered before the, can you post it there before the TUT? And you can ask me as well, and then I can make sure that those are some of the questions that I'll try to go through in the tutorial. It'll help to give a bit of focus. But in general, guys, work hard and study hard. I think you guys have probably had enough maths for a Friday afternoon. And yeah, thanks for coming through. I'm gonna stop sharing screen just to try reduce data as well. But yeah, thanks for coming through. And you guys oh, actually, oh, I've got a list of everyone who's attended here too. Yeah, thanks so much. Have a good weekend, guys. Thanks.